A million miles from our planet, a remarkable piece of technology is quietly transforming our understanding of the cosmos. The James Webb Space Telescope, a marvel of engineering, is revealing sights that were once thought impossible to witness. It has captured images of galaxies that emerged just 290 million years after the universe began, black holes with masses greater than entire galaxies, and stars detonating at the very edge of time. The light from these distant objects has been traveling for over 13 billion years, carrying with it stories from the dawn of everything. What you're about to experience are findings that don't just add to our knowledge, they challenge the very foundations of physics as we know them. If you're ready to see the universe in a way no one has before, this is your invitation to join the journey. Suspended in the vast darkness, a machine roughly the size of a tennis court orbits a unique point in space, not around Earth like its predecessor Hubble, but at a location where the gravitational pull of the Earth and Sun balance perfectly. This spot, known as the second Lagrange point, is where Webb keeps its steady vigil. The telescope itself is a feat of human ingenuity, costing $10 billion and requiring 2 decades to bring from concept to reality. Its mirror, composed of 6 gold-coated hexagonal segments, unfolds in space with the precision of origami, each panel designed to catch the faintest glimmers of light that have traveled across the universe since it was in its infancy. Unlike Hubble, which observes invisible and ultraviolet light, Webb is tuned to the infrared. This is crucial because as the universe expands, the light from the most distant galaxies is stretched, shifting from visible blue and ultraviolet into the infrared spectrum. Hubble's instruments, limited to visible light, simply couldn't see this far. Webb, however, is designed to peer into these longer wavelengths, revealing what was previously hidden from view. The telescope's journey began on Christmas Day, 2021. For 6 tense months, engineers and scientists watched as over 1,000 mechanisms had to function flawlessly. Any single failure could have doomed the mission, but everything worked as planned. The mirror unfolded, the sunshield deployed, and the instruments came to life. When Webb finally opened its eye, it looked further back in time than any device before it. Every observation Webb makes is like looking through a time machine. When we see a galaxy a billion light years away, we're seeing it as it was a billion years ago, because that's how long its light took to reach us. Webb pushes this concept to the extreme, capturing photons that began their journey when the universe was less than 5% of its current age. These ancient galaxies appear as faint, reddish smudges against the blackness, their light having traveled for more than 13 billion years. We're not just seeing distant objects, we're witnessing the birth of the cosmos itself. Before Webb, scientists had a clear idea of what the earliest galaxies should look like: small, faint, and simple. The universe, they thought, was too young for anything complex to have formed, but Webb's first images shattered these expectations. The galaxies it found were too large, too bright, and too developed for their age. Some had already formed massive structures that, according to previous models, should have taken billions of years to assemble. One astronomer described the findings as completely unexpected, while another suggested they might force a rewrite of cosmology itself. The standard model of the universe predicted one thing. Webb showed something entirely different. Each new image revealed galaxies that didn't fit the textbook narrative, and every spectrum told a story that defied established theory. When your most advanced instrument shows you the impossible, the only thing to do is keep looking. And what Webb found next was even more astonishing. In its first deep field images, astronomers noticed a tiny red dot. Initially, it was just another data point, labeled and set aside. But when someone analyzed the numbers, they realized the light from this galaxy had been stretched by a factor of 15. This meant it existed just 290 million years after the Big Bang, when the universe was only about 2% of its current age. The galaxy, nicknamed Jades, spans more than 1/600 light years and glows with the light of newly forming stars. It's so bright that Webb could have detected it even if it were 10 times fainter, suggesting that many more galaxies from this era are waiting to be discovered, perhaps even older ones, formed within the first 200 million years. This discovery posed a serious problem for existing theories. According to standard cosmology, galaxies grow slowly, starting as small clumps of matter within halos of dark matter. Gravity pulls in gas, stars ignite, and over billions of years, galaxies merge and grow larger. But JWST didn't follow this script. It was too luminous, too organized, and too large for its age. Computer simulations had predicted that early galaxies would be dim, chaotic, and tiny. JWST was none of these things. Its light came from young stars, not from a black hole, making it even more puzzling. Black holes can produce intense brightness from a small region, but star formation takes time that JWST shouldn't have had. Other early galaxies showed the same pattern, bigger and brighter than they should be. One astronomer compared it to finding a fully grown adult where you expected a newborn. The universe simply didn't have enough time for these structures to form through conventional processes. Some scientists suggested that galaxy formation must have happened faster in the early universe, or that stars formed more efficiently back then. Maybe dark matter halos collapsed more quickly. These ideas help, but they don't fully explain what Webb is seeing. The galaxies are still too extreme. Another possible explanation involves the initial conditions of the universe. Maybe the Big Bang didn't distribute matter evenly, and some regions started out denser than others, allowing galaxies to form faster there. But this raises new questions. Why would those dense regions exist, and what created them? The discovery of JWST extended our view of cosmic history by 40% in just 18 months of observations. Every new galaxy found at these distances adds another piece to a puzzle that refuses to fit together. One researcher admitted that these machines were built not just to confirm what we thought we knew, but to break the paradigm. They just didn't know how it would break, and then Webb found something that made even these massive galaxies seem like a minor issue. In the universe we know today, there's a well-established rule. For every 10 solar masses of stars in a galaxy, there's typically about one solar mass in the central black hole. This ratio holds true across the cosmos, from our own Milky Way to the nearest galaxies. It's so consistent that astronomers have built entire theories of galaxy evolution around it. But when Webb turned its gaze to the early universe, this rule was shattered. Astronomers discovered a galaxy from when the universe was just 570 million years old. They measured the mass of its stars, then compared it to the mass of the black hole at its center. The result was astonishing. The black hole made up a full 10% of the galaxy's stellar mass. For every 10 solar masses of stars, there was one solar mass in the black hole. This broke the established ratio by a factor of 1,000. Scientists call these overmassive black holes, but even that term doesn't capture how extreme these objects are. Imagine if your heart weighed a tenth as much as your entire body. That's the kind of imbalance seen in these early galaxies. The black hole isn't just a central feature, it dominates the entire system. Webb has found dozens of such objects, appearing as tiny red dots in its deep field images. The red color comes from hot gas spiraling into the black hole, heating up to millions of degrees and radiating energy. This creates a compact, blazing core that outshines the surrounding stars. This discovery has forced astronomers to rethink everything they thought they knew about how galaxies and black holes grow together. In the nearby universe, black holes and their host galaxies seem to grow in tandem, maintaining that 1 to 10,000 ratio. The relationship is so reliable that it's become a cornerstone of modern astrophysics, but these early galaxies show a completely different pattern. The black holes grew first, and they grew fast, becoming massive before their host galaxies had time to form many stars. One researcher described it as a baby with the heart of a giant. The proportions are all wrong. How could these black holes have become so large so quickly? There are two main ideas. The first is that they started as the remnants of massive stars. When such stars die, they collapse into black holes, which then grow by consuming nearby matter. But this process takes time. Even if a black hole devours material at the fastest possible rate, it would still take hundreds of millions of years to reach millions of solar masses. The second idea is that some black holes were born big, forming directly from the collapse of enormous clouds of gas, bypassing the stellar stage entirely. These primordial, Black holes could start out with thousands or even millions of solar masses. Webb's data now leans toward this second scenario. Several observations suggest that these massive black holes couldn't have grown from stellar seeds in the time available. They must have started out large. But this raises new mysteries. What special conditions would allow a gas cloud to collapse directly into a black hole rather than forming stars first? The story gets even stranger when you look at where these overmassive black holes are found. They're not scattered randomly across the early universe. Instead, they sit in a vast network, the cosmic web. This is the large-scale structure of the universe, where galaxies gather along filaments of dark matter, like beads on invisible strings. Astronomers mapping the early universe have found that these little red dots cluster together in specific locations within the cosmic web. More evolved galaxies appear at the intersections of filaments, while less developed ones are scattered along the filaments themselves. The overmassive black holes are not the most massive structures, but they are among the most active, consuming matter at ferocious rates. In one survey, 7 such objects from when the universe was 5 billion years younger than today all showed the same pattern, a central black hole with a mass about 10% that of the stars in the galaxy. This consistency suggests that these are not just rare oddities, but a distinct population of early universe objects. As these black holes feed, they emit powerful radiation that pours into the surrounding gas, heating it and pushing it away. Astronomers call this process feedback. In nearby galaxies, feedback from black holes helps regulate star formation. Too much feedback and new stars can't form, too little and stars form so rapidly that the galaxy runs out of gas. In these early galaxies, feedback might explain why the galaxies stayed small. The black holes turned on early, blasting their surroundings with energy and preventing the galaxy from forming many stars. Only after the black hole quieted down could gas cool and form stars at normal rates, gradually restoring the ratio seen in modern galaxies. But there's a timing problem. If black holes form first and prevent star formation, where did the black holes get their mass? They need gas to grow, but if they're blasting all the gas away, how did they become so massive in the first place? Some researchers propose a burst scenario. The black hole forms and rapidly grows, consuming huge amounts of gas before feedback becomes strong enough to push material away. During this brief window, the black hole can reach millions of solar masses, then feedback kicks in, shutting down both black hole growth and star formation. Later, the system settles into a calmer state. Others point to mergers as a solution. If two galaxies collide, their central black holes can merge, instantly creating a more massive black hole. In the early universe, galaxies were closer together, making mergers more common. Webb has already found evidence of merging black holes in the early universe, supporting this idea. Recent observations add another twist. Some overmassive black holes are found in regions with surprisingly low levels of heavy elements. Stars create heavy elements when they die, enriching the surrounding gas. A galaxy with many stars should show high levels of these elements, but some of these black hole hosts show low enrichment, suggesting few stars have lived and died there. This fits the primordial black hole theory. If the black hole formed directly from pristine hydrogen and helium, it wouldn't need previous generations of stars. Each new spectrum Webb captures adds more detail to this evolving picture. What's clear is that the early universe operated very differently from the one we see today, and the surprises don't end with black holes. About 350 years ago, a star exploded, sending a flash of light racing outward at the speed of light. In 2025, that light reached a cloud of interstellar dust and gas, and Webb was watching. When the supernova's light finally arrived at a distant cloud of dust and gas, the James Webb Space Telescope was ready to capture the event. The flash illuminated the cloud from within, and Webb's sensitive instruments recorded the glow in remarkable detail. What appeared in the images was unlike anything astronomers had expected. Instead of a diffuse, formless haze, the illuminated dust revealed intricate structures, knots, filaments, and layers that resembled the grain of polished wood. These sheets of material, some just 400 astronomical units across, were far more organized and tightly packed than anyone had imagined. For context, that's only a fraction of a light year, and yet these features are several times larger than our entire solar system. Astronomers refer to this phenomenon as a light echo. It's similar to how sound bounces off canyon walls, but in this case, it's a pulse of light reflecting and scattering off interstellar material. The supernova's flash acts like a cosmic spotlight, briefly revealing structures that would otherwise remain hidden in the darkness. As the light continues to expand outward, it sequentially illuminates more distant regions, creating a moving echo that can be tracked over time. The particular light echo Webb observed was near the remnants of a supernova in the constellation Cassiopeia. This remnant is the shattered shell of a star that exploded centuries ago, but Webb wasn't focused on the remnant itself. Instead, it targeted the unrelated dust and gas in the background, which just happened to be in the right place at the right time to be lit up by the ancient explosion. The level of detail in the illuminated dust shocked the research team. They had expected to see a smooth, featureless cloud, but instead found a complex, layered structure. One scientist likened it to peeling an onion, with nested shells stacked upon each other in elaborate patterns. Some of these sheets appeared to be shaped by magnetic fields threading through space, aligning the dust into parallel formations. This discovery is significant because it changes our understanding of the space between stars. The interstellar medium, the vast expanse between stars, is not empty. Every cubic meter contains atoms of gas and tiny grains of dust, most of which clump together in clouds. These clouds are the birthplaces of new stars, and understanding their internal structure is crucial for unraveling the mysteries of star formation. Before Webb, astronomers could only study the outer surfaces of these clouds. Now, for the first time, they can peer inside and see the fine structure within. The sheets and filaments Webb observed are several times larger than our solar system, yet they are just small features within much larger clouds. Why does the material organize itself into sheets rather than random blobs? One explanation involves magnetic fields. The interstellar medium is threaded with magnetic lines of force, and charged particles and dust grains tend to align along these fields. Over time, this creates elongated, organized structures. Turbulence in the gas also plays a role, stirring the material into complex patterns. Researchers now believe that most dense, dusty regions in space probably look like this on the inside. Every molecular cloud, every star-forming region, likely contains similar layered structures. Webb's observations have provided a new template for understanding the three-dimensional architecture of interstellar space. These findings also shed light on how matter moves between stars. The sheets may act as channels, guiding the flow of gas along specific paths. Where sheets intersect or compress, conditions may become favorable for star formation. Understanding this process helps astronomers predict where new stars are likely to ignite. The light echo technique opens a new window for studying the interstellar medium. Astronomers can wait for supernova or other bright, transient events to illuminate different regions of space, then use Webb to observe the revealed structures. Each echo provides a snapshot of a different volume of interstellar space, gradually building a three-dimensional map of the galaxy's hidden architecture. While Webb was studying the space between stars in our own region of the galaxy, it was also observing the deaths of stars in the most distant reaches of time. On March 14, 2025, a space-based observatory detected a sudden burst of gamma rays, a flash of high-energy light lasting only a few seconds. Within hours, telescopes around the world turned to observe the fading afterglow. The light revealed something extraordinary. This explosion had occurred when the universe was just 730 million years old. The burst originated from a massive star at the end of its life. Stars much larger than our sun leave fast and die violently. When they exhaust their nuclear fuel, their cores collapse in less than a second, triggering a supernova explosion. In the most massive stars, the collapse also generates jets of material that punch through the star at nearly the speed of light, producing gamma rays, the most energetic form of light. When one of these jets happens to point toward Earth, we detect it as a gamma ray burst. This particular burst set a new record for distance. The light had been traveling for more than 13 billion years, allowing astronomers to witness a star's death during the epoch known as reionization, when the first stars and galaxies were clearing away the fog of neutral hydrogen that filled the early universe. The discovery was not a fluke. Ground-based telescopes confirmed the extreme distance using spectroscopy, but the most crucial observations came 110 days after the burst, when Webb focused on the region. By then, the initial flash had faded, leaving only the supernova itself, a slower, dimmer event. Webb's sharp infrared vision made it possible to separate the fading light of the supernova from the faint glow of its host galaxy. This is a challenging task, as the supernova outshines its host by a significant margin, and both appear as a single point of light from Earth. But Webb's capabilities allowed astronomers to identify both the explosion and the galaxy that hosted the dying star. What they found was surprising. The ancient supernova looked remarkably similar to supernova in the modern universe. Astronomers compared it to a well-studied nearby supernova from 1998 and found that the brightness, spectrum, and evolution over time matched closely. Despite occurring in a vastly different environment, the explosion followed the same basic physics. This is both reassuring and puzzling. It suggests that the laws of physics have remained unchanged over cosmic time, but it also raises questions about why the early universe, with its different conditions, produces such familiar results. The host galaxy itself was small and faint, barely detectable even with Webb. This tells us that massive stars were forming and dying in some of the smallest galaxies, which may have served as the building blocks for larger structures over time. Each distant supernova acts as a beacon, briefly illuminating its surroundings and allowing astronomers to study the gas and dust around the dying star. This provides a glimpse into the conditions of the interstellar medium billions of years ago. Gamma-ray bursts paired with supernova also test models of how massive stars evolve. The close match between this ancient supernova and modern ones supports current theories, but it also raises new questions about the role of heavy elements in stellar evolution. Even as this star was exploding in isolation elsewhere in the early universe, black holes were not dying alone. In another corner of the early universe, astronomers using Webb's powerful vision noticed something unusual in a galaxy known as JWST, which existed just 740 million years after the Big Bang. When they examined the images, they saw not one, but two bright cores within the same galaxy. At first, this was puzzling. Was it a single galaxy with an odd structure, or two galaxies in the process of merging? To find out, scientists turned to Webb's spectroscopic data, which can reveal the motion and composition of gas near these bright points. The spectra showed gas moving at incredible speeds, hundreds of kilometers per second, swirling in tight orbits around both cores. This is the unmistakable signature of matter falling into black holes. As gas accelerates toward a black hole, it heats up to millions of degrees, emitting light at specific wavelengths. Both cores in JWST displayed this telltale sign, confirming that the galaxy contained not one, but two supermassive black holes, each actively feeding on surrounding material. This was the earliest black hole merger ever detected. The two black holes are locked in a gravitational dance, spiraling closer together as they lose energy through gravitational waves, ripples in the fabric of space-time predicted by Einstein's theory of general relativity. Eventually, they will collide and merge into a single, even more massive black hole. Webb's sharp imaging allowed astronomers to distinguish the two black holes as separate entities, something ground-based telescopes could never do at such distances. Before Webb, even space telescopes lacked the sensitivity and resolution to study such distant, faint objects in detail. The discovery of this early merger has profound implications for our understanding of how supermassive black holes grow. Most large galaxies today, including our own Milky Way, harbor a supermassive black hole at their center. But how did these cosmic giants reach such enormous sizes? One key mechanism is merging. When two galaxies collide, their central black holes eventually sink to the center of the merged system and combine. If mergers were rare in the early universe, black holes would have to grow mainly by swallowing gas, a slow process. But finding mergers like the one in ZS7 so early in cosmic history suggests that these events were common enough to accelerate black hole growth dramatically. The two black holes in ZS7 are not yet touching. They orbit each other, gradually losing energy and spiraling inward. This process takes millions of years as gravitational waves carry away orbital energy. When the black holes finally merge, the collision will unleash a powerful burst of gravitational waves. While current detectors on Earth can only sense mergers of smaller black holes in the nearby universe, future space-based observatories will be able to detect the gravitational waves from supermassive black hole mergers at high redshift. These observations will reveal how often such events occurred and how much they contributed to the growth of black holes in the early universe. The ZS7 system also sheds light on how galaxies themselves merge and evolve. When galaxies collide, their stars, gas, and dark matter interact in complex ways. Stars rarely collide directly, since the space between them is vast, but gas clouds can crash together, triggering bursts of star formation. The collision compresses the gas, making it dense enough to ignite new stars. Over time, the two galaxies merge completely, forming a single, more massive galaxy. The central black holes take longer to merge, as they must lose angular momentum through interactions with stars and gas before finally coalescing. The stellar mass of ZS7 is similar to that of the Large Magellanic Cloud, a small galaxy orbiting the Milky Way. Imagine if the Large Magellanic Cloud contained not one, but two supermassive black holes as large as the one at the center of our galaxy. The dynamics of the entire system would be dominated by these black holes. This is what astronomers see in ZS7. Finding such a merger so early in cosmic history suggests that the processes shaping galaxies and black holes today were already at work in the universe's first billion years. But the surprises didn't stop there. As astronomers continued to study the most distant galaxies, they encountered another puzzle. The light from these remote objects has been traveling for so long that the universe has expanded significantly during its journey. This expansion stretches the light, a phenomenon known as redshift. Astronomers use redshift as a measure of how much the universe has grown since the light was emitted. A redshift of 1 means the wavelength has doubled. A redshift of 2 means it has tripled, and so on. The galaxy JWST, for example, has a redshift of 1432. This means the light from JWST has been stretched by a factor of over 15. Ultraviolet light that left the galaxy billions of years ago now arrives at Webb as infrared. This is why infrared telescopes are essential for studying the early universe. The light has shifted so far toward the red that visible light telescopes can't detect it. Measuring redshift requires splitting the incoming light into its component wavelengths, creating a spectrum. Certain elements in the galaxy produce emission or absorption lines at specific wavelengths. By comparing where these lines appear in the observed spectrum to where they should be, astronomers can calculate how much the light has been stretched. For JWST, hydrogen emission lines that should appear in the ultraviolet are now seen in the infrared, leaving no doubt about the galaxy's ancient origin. The expansion of the universe also complicates how we think about distance. When astronomers say a galaxy is 13.5 billion light years away, they mean the light has been traveling for that long. But because space itself has been expanding, the actual distance to the galaxy now is much greater. This co-moving distance takes into account the growth of the universe during the light's journey. Redshift provides a more fundamental measurement than distance, directly indicating how much the universe has expanded since the light was emitted. A redshift of 14 means the universe has grown by a factor of 15 since that light left its source. This stretching not only changes the color of the light but also dims it, as photons arrive with less energy and are more spread out in time and space. Webb compensates for this dimming with its enormous mirror and ultra-sensitive detectors, cooled to just a few degrees above absolute zero to minimize noise. Even so, observing the most distant galaxies requires hours or even days of exposure time. The deep field observations that revealed JWST, for instance, totaled more than 70 hours of telescope time, a huge investment for a facility where every hour is precious, but the payoff is immense. Each new galaxy found at these extreme distances adds another piece to the puzzle of cosmic history, revealing a universe that is brighter, more active, and more complex than anyone had predicted. The record for the most distant known galaxy keeps advancing. Before JADES, the record was held by a galaxy at redshift 13. 2. JADES pushed it to 14. 32, and astronomers expect even more distant galaxies to be discovered as Webb continues its mission. The search for the universe's earliest structures is far from over, and each new discovery brings us closer to understanding how everything began. The expansion of the universe is not just a curiosity, it's a fundamental property that shapes everything we see. Astronomers measure this expansion using a value called the Hubble constant, which tells us how fast galaxies are moving away from each other for every unit of distance. The current best estimates put this number at about 70 kilometers per second per megaparsec. In practical terms, that means a galaxy 3 million light years away is receding at 70 kilometers per second, while one twice as far is moving away at 140 kilometers per second. This relationship is linear, and it's one of the cornerstones of modern cosmology. But there's a problem. There are two main ways to measure the Hubble constant, and they don't agree. The first method looks at the cosmic microwave background, the faint afterglow of the Big Bang, now stretched into microwaves by the expansion of space. By analyzing the patterns in this ancient light, cosmologists can infer the composition and geometry of the early universe and predict how fast it should be expanding today. This approach yields a value of about 67.4 kilometers per second per megaparsec. The second method uses observations of nearby galaxies, particularly those containing certain types of supernova. These stellar explosions have a known intrinsic brightness, so by measuring how bright they appear from Earth, astronomers can calculate their distance. Combining these distances with measurements of how fast the galaxies are moving away gives a direct measurement of the Hubble constant. This method consistently produces a higher value, around 73 kilometers per second per megaparsec. The difference between these two measurements is small in absolute terms, but it's large enough to be significant. This disagreement, known as the Hubble tension, has persisted despite years of increasingly precise observations and careful cross-checks. Some scientists hoped that Webb's new data would resolve the issue, perhaps by revealing a subtle error in one of the methods, but Webb's observations have only deepened the mystery. Its measurements of nearby supernovae confirm the higher value found by the Hubble Space Telescope, suggesting that the tension is real and not the result of an instrumental bias. So what could explain this discrepancy? One possibility is that our understanding of the early universe is incomplete. The cosmic microwave background method relies on a specific cosmological model. If that model is missing something, perhaps a new form of dark energy or a change in the behavior of gravity on large scales, then the predicted expansion rate could be off. Another idea is that our local region of the universe is somehow unusual, expanding faster than average. But surveys of our cosmic neighborhood suggest we live in a fairly typical patch of space. A third possibility is that the universe's expansion rate has changed over time in a way that current models don't account for. The cosmic microwave background shows us the universe as it was 380 years after the Big Bang, while supernova measurements probe the last few billion years. If something happened in between, an unknown event or a shift in the properties of dark energy, it could explain the discrepancy. Some theorists have even proposed that gravity itself behaves differently on the largest scales, requiring a modification of Einstein's general relativity. But such radical ideas need strong evidence. Webb's data has ruled out some simpler explanations. For example, some researchers thought the Hubble Space Telescope's measurements might be skewed by a subtle instrumental error. But Webb uses entirely different instruments and techniques, and it gets the same answer. That means the tension is not an artifact of the equipment. The mystery remains unsolved, and resolving it may require a breakthrough in our understanding of fundamental physics. While astronomers wrestle with the Hubble tension, Webb is also helping to answer another profound question. What were the first stars in the universe like? The earliest stars, known as population Roman 3 stars, are thought to have formed from pristine gas, hydrogen, helium, and a trace of lithium created in the Big Bang. These stars would have contained no heavier elements because those elements are forged in the hearts of stars and spread through the universe by supernovae. Every star we've ever observed contains at least some heavy elements, so population Roman 3 stars have never been seen directly. But theory insists they must have existed because someone had to make the first heavy elements. Without heavy elements to help cool the gas, the first star forming clouds would have remained hot and resisted collapse. Only the most massive clouds could overcome this resistance, leading to the formation of extremely massive stars, perhaps 50 to 500 times the mass of our Sun. These giants would have burned bright and died young, living only a few million years before exploding as supernova and seeding the cosmos with the first heavy elements. The next generation of stars would then form from this enriched gas, gradually building up the chemical complexity needed for planets and life. Population Roman 3 stars should have vanished billions of years ago, but if we look far enough back in time, we might catch a glimpse of them. Webb is capable of observing galaxies from when the universe was less than 500 million years old, early enough that some population Roman 3 stars might still have been shining. Detecting them is incredibly difficult because a single massive star is too faint to see across billions of light years. Instead, astronomers look for the collective signature of many such stars in a galaxy's spectrum. Pure hydrogen and helium stars produce different emission lines than stars with heavier elements. Certain lines should be strong while others are weak or absent. Webb's observations of a galaxy called JWST 11, which existed 430 million years after the Big Bang, have provided tantalizing hints. The spectra from its outer regions show strong hydrogen emission with unusual ratios between different lines, patterns that match predictions for regions where population Roman 3 stars are forming. The evidence isn't definitive, and other processes could produce similar features, but the possibility is exciting. If confirmed, it would be the first direct detection of the stars that brought light to the universe and began the process of cosmic chemical enrichment. These primordial stars also played a crucial role in reionizing the universe. After the Big Bang, the universe was hot and ionized, but as it cooled, electrons and protons combined to form neutral hydrogen, plunging the cosmos into darkness. When the first stars ignited, their ultraviolet radiation ionized the hydrogen around them, creating bubbles of ionized gas. As more stars formed, these bubbles grew and merged, eventually reionizing the entire universe and allowing light to travel freely through space. Webb is systematically searching for these ancient objects, imaging and obtaining spectra of hundreds of early galaxies, even if only a small fraction of them still host population Roman 3 stars. The surveys should eventually find them. Discovering these stars would connect us directly to the universe's first chapter, revealing the origins of all the elements that make planets and life possible. While astronomers hunt for the universe's first stars, Webb has also uncovered objects that defy easy explanation. In its deep field images, the telescope has revealed a population of compact, intensely red points scattered across the early universe. These enigmatic objects, which astronomers have dubbed little red dots, are both common and mysterious. They appear at redshifts between 5 and 8, meaning they existed when the universe was just 1 to 2 billion years old. Their red color comes from hot gas swirling around a central black hole, heated to millions of degrees as it spirals inward. This process creates an accretion disk that glows across the electromagnetic spectrum, but the specific shade of red we see depends on the temperature of the gas and the amount of dust surrounding the system. What makes these little red dots so puzzling is not just their abundance, but their spectral signatures. When astronomers split their light into its component wavelengths, they find a mix of features: broad emission lines that indicate gas moving at thousands of kilometers per second near a black hole, and narrower lines associated with star-forming regions. Normally, these two signatures come from different types of objects. Active galactic nuclei powered by supermassive black holes show broad lines, while star-forming galaxies show narrow ones. The little red dots display both at once, suggesting a complex interplay between black hole activity and star formation. Their compactness adds to the mystery. Even with Webb's sharp vision, these objects appear almost point like with emission coming from regions less than 1,000 light years across. For comparison, the Milky Way is about 100,000 light years wide. These little red dots pack enormous energy into a tiny volume, making them some of the most extreme environments in the early universe. Scientists have proposed several explanations. Some think little red dots are simply quasars, supermassive black holes surrounded by thick clouds of dust that absorb visible and ultraviolet light, re-emitting it as infrared. Others suggest they represent a brief transitional phase in galaxy evolution, where a galaxy is in the process of forming its first supermassive black hole. In this scenario, the black hole has just switched on and is rapidly consuming gas, while the host galaxy is still actively forming stars. Eventually, the black hole's energy output would suppress star formation, and the object would evolve into a typical quasar. A third idea is that these objects form in special environments, such as dense regions of the cosmic web where gas flows and galaxy interactions are more common. Webb's observations are helping to test these theories. By collecting detailed spectra of many little red dots, astronomers can measure properties like black hole mass, star formation rate, dust content, and chemical composition. One recent study examined 7 little red dots from the same era and found that all had overmassive black holes, about 10% the mass of their host galaxy's stars. This consistency suggests that little red dots are not just rare oddities, but a real population with shared characteristics. Their existence challenges models of black hole formation, implying that the processes creating them must be both robust and efficient. Another puzzle involves the faint galaxies that sometimes surround these bright cores. When Webb images the regions around little red dots with extreme sensitivity, it occasionally detects a faint, extended glow. This shows that the compact red core sits within a much larger, dimmer galaxy. The relationship between the brilliant nucleus and its faint host is still unclear, but understanding it will reveal how black holes and galaxies co-evolve. The abundance of little red dots also has implications for the structure of the universe itself. The cosmos is not a uniform expanse. Matter clumps together under gravity, forming a vast network known as the cosmic web. Galaxies gather along filaments of dark matter, creating chains that stretch across hundreds of millions of light years. Where filaments intersect, massive galaxy clusters form, while vast voids lie between them. This structure emerged from tiny fluctuations in density present just after the Big Bang, which grew over billions of years into the web we see today. Webb's ability to map galaxies at extreme distances allows astronomers to reconstruct what the cosmic web looked like when the universe was less than 2 billion years old. Even at Redshift 8, when the universe was under 1 billion years old, galaxies already clustered along filaments, showing that the basic architecture of the cosmic web was established early. What changed over time was the thickness of the filaments and the mass of the clusters at their intersections. Understanding how this structure evolved helps constrain cosmological models. The rate at which the web grows depends on the properties of dark matter and dark energy. Too little dark matter and structure forms too slowly, too much, and it forms too quickly. The observed evolution of the cosmic web provides a crucial test for these models. Dark matter, which makes up about 85% of all matter in the universe, forms the skeleton of the web. Galaxies form where dark matter is densest, tracing its invisible framework. Webb cannot see dark matter directly, but by mapping the distribution of galaxies, it can infer the underlying dark matter structure. Simulations of the universe's evolution, starting from the conditions after the Big Bang, predict the detailed structure of the cosmic web. When these simulations match observations, it confirms our understanding of dark matter and gravity. Discrepancies suggest missing physics or more complex galaxy formation processes. The cosmic web also influences the properties of individual galaxies. Galaxies in dense regions evolve differently from those in voids. In crowded environments, interactions and mergers are more frequent, triggering bursts of star formation and fueling black hole growth. In contrast, galaxies in underdense regions evolve more quietly. Webb's data show that little red dots tend to cluster in moderately dense regions along filaments, hinting that their formation may require the right combination of gas supply and frequent interactions. Mapping the cosmic web at different epochs also reveals how matter flows through the universe. Gas streams along filaments toward galaxy clusters, feeding star formation in galaxies along the way. When gas reaches a cluster, it can be heated by shocks and turbulence, shutting down star formation. Webb can observe these processes in action, providing a dynamic view of how the universe's largest structures shape the evolution of galaxies. Yet, even as the cosmic web takes shape, the galaxies within it behave in unexpected ways. Measurements show that early galaxies are much denser than those we see today. Some are 1,000 times denser, packing the same mass of stars into a much smaller volume. This creates a paradox. If galaxies start small and dense, but end up large and diffuse, something must cause them to expand over time without gaining much mass. Theories suggest that mergers, changes in dark matter halos, and feedback from supernova and black holes all play a role, but the details are still being worked out. Webb's higher resolution images confirm that early galaxies are indeed more compact than expected, and their evolution remains one of the great puzzles of modern astronomy. Understanding how these dense, bright, and active galaxies transform into the sprawling systems we see today is key to unraveling the story of cosmic evolution. The more astronomers studied the early universe with Webb, the more they realized that the cosmos at cosmic dawn was not a quiet, dim place. Instead, it was ablaze with star formation, filled with galaxies that shone far brighter than anyone had predicted. Take the galaxy Jades, for example. Given its distance, over 13 billion light years away, its light should be faint, stretched, and diluted by the expansion of space. Yet, Jades is surprisingly luminous, so much so that Webb could have detected it even if it were 10 times dimmer. This raised a fundamental question. If such a bright galaxy is easy to spot, why aren't there more like it? The answer, it turns out, is that there are. Webb has found numerous bright galaxies at high redshift, far more than pre-launch models anticipated. These discoveries have forced astronomers to rethink their assumptions about the early universe. The first galaxies were not hiding in the darkness, they were active, forming stars at astonishing rates. Measuring a galaxy's brightness gives a direct clue to its star formation rate. The more young, massive stars a galaxy contains, the more ultraviolet light it emits, making it appear brighter even across vast distances. By correcting for distance and redshift, astronomers estimate that Jades is forming dozens of solar masses worth of new stars every year. For comparison, the Milky Way currently forms only about 1 or 2 solar masses of stars per year. Jades, despite being much smaller, is tens of times more productive. The size of these early galaxies adds to the puzzle. Jades, for instance, is over 1/600 light years in diameter, much larger than models predicted for galaxies at this epoch. Simulations had suggested that galaxies forming just a few 100 million years after the Big Bang would be tiny, perhaps only a few hundred light years across. Instead, Webb is finding galaxies that are not only larger, but also more structurally developed than expected. What makes a galaxy bright is ultimately the number of young, massive stars it contains. These stars burn hot and fast, flooding their galaxies with ultraviolet light. So the mystery of brightness is really a question about star formation. Why did early galaxies form stars so efficiently? One factor is the abundance of gas. In the early universe, galaxies were rich in hydrogen and helium, with little of their gas yet converted into stars. This provided ample fuel for rapid star formation. The gas was also pristine, flowing into galaxies along the filaments of the cosmic web, ensuring a steady supply. Another factor is the lack of dust. In the modern universe, dust grains formed from heavy elements help cool gas clouds, making star formation easier. But dust also absorbs ultraviolet light, dimming galaxies. Early galaxies with little dust let more starlight escape, making them appear brighter than their modern counterparts. Feedback mechanisms, like supernova explosions and black hole winds, also play a role. In nearby galaxies, these processes regulate star formation by heating or expelling gas. In the early universe, feedback may have been weaker, allowing star formation to proceed at higher rates. Even with these explanations, simulations still struggle to produce galaxies as bright as those Webb observes. Some researchers propose that the luminosity is temporarily boosted by starburst phases, brief periods of intense star formation triggered by galaxy mergers or large inflows of gas. During these bursts, a galaxy can shine far brighter than its long-term average. If Webb happens to catch galaxies during these rare luminous phases, it would explain why so many appear brighter than expected. Another possibility involves the initial mass function, the distribution of stellar masses when stars form. In the local universe, most stars are low mass with only a few massive stars. If the early universe favored the formation of more high mass stars, the total ultraviolet output per unit mass would be higher, making galaxies appear brighter without requiring more total star formation. Testing these ideas requires detailed observations of many galaxies, and Webb is conducting large surveys to build up the necessary statistics. The implications of these findings extend beyond galaxy formation. Bright star-forming galaxies produce more ionizing photons, which could have reionized the universe faster than previously thought. Webb's observations of galaxies from the reionization era will help test this idea, revealing how quickly the universe transitioned from opaque to transparent. While Webb's primary mission is to study the distant universe, its capabilities have also opened new windows on our cosmic neighborhood. One of the most intriguing discoveries came from observations of Alpha Centauri, our closest stellar neighbor. This system, just over 4 light-years away, consists of 3 stars, Alpha Centauri A and B, which are similar to our Sun, and Proxima Centauri, a small red dwarf. Proxima is already known to host at least 2 planets, one of which orbits in the habitable zone where liquid water could exist. Detecting planets around Alpha Centauri A and B has been much more challenging. These stars are bright, and their glare overwhelms the faint signals from any orbiting planets. Ground-based telescopes have struggled to find evidence of planets in this system. But Webb, with its mid-infrared instrument and innovative observing strategies, has changed the game. By carefully blocking out the starlight and searching for faint infrared sources, astronomers detected a possible planet orbiting Alpha Centauri at about twice Earth's distance from the star. The signal is consistent with a large planet, possibly a gas giant, though further observations are needed to confirm it. If this detection is real, it would represent our closest planetary neighbor outside the solar system, aside from Proxima's small worlds. The proximity of Alpha Centauri makes it a prime target for future missions, including the possibility of direct imaging or even robotic exploration. Detailed studies of any planets in this system would provide invaluable insights into planet formation and the potential for habitability in systems similar to our own. The technique used to detect the possible planet around Alpha Centauri demonstrates Webb's versatility. Although designed to study the most distant galaxies, the telescope can also be adapted to search for planets around nearby stars. This expands Webb's scientific reach and ensures that unexpected discoveries can come from even the most familiar corners of the sky. If confirmed, the planet around Alpha Centauri A would likely have formed through the same process that built Jupiter and Saturn in our solar system, the gradual accumulation of a solid core, followed by the rapid accretion of gas from the surrounding disk. The planet's location in the habitable zone raises the tantalizing possibility that it could host large moons, some of which might be suitable for life. Detecting such moons would require even more advanced telescopes, but the discovery would mark a major milestone in the search for habitable worlds beyond our solar system. The Alpha Centauri system also serves as a test case for theories of planet formation. By comparing planets around stars similar to our Sun, astronomers can determine which aspects of our solar system are typical and which are unique. This context is essential for understanding how common planetary systems like ours might be throughout the galaxy. Webb's ability to reveal new worlds, both near and far, underscores its role as a transformative tool for astronomy. Whether it's uncovering the secrets of the first galaxies or finding planets next door, the telescope is reshaping our view of the universe at every scale. While Webb's discoveries about distant galaxies and nearby planetary systems have captured headlines, Some of its most profound insights come from studying the space between stars. The interstellar medium, the gas and dust that fills the voids within galaxies, has long been a subject of fascination and mystery. Before Webb, astronomers pictured these regions as mostly smooth and featureless, with only hints of turbulence and structure. But Webb's infrared vision, especially when combined with the light echo technique, has revealed a hidden world of complexity. When a supernova explodes, its light can travel for centuries before encountering a cloud of interstellar dust. When this happens, the light illuminates the dust from within, creating a light echo that briefly reveals the internal structure of the cloud. Webb's observations of such echoes have shown that the interstellar medium is anything but uniform. Instead, it is filled with tightly packed sheets, filaments, and knots, structures as small as 400 astronomical units across, several times the size of our solar system, but still tiny compared to the vastness of space. These sheets are not random. Magnetic fields thread through the interstellar medium, and as charged particles and dust grains move, they tend to align along these invisible lines of force. Over time, this interaction sculpts the gas and dust into elongated, layered formations. Turbulence driven by supernova explosions, stellar winds, and gravitational instabilities stirs the material further, creating a hierarchy of structures from the largest clouds down to the smallest eddies. Understanding these structures is crucial for unraveling the process of star formation. Stars are born when dense regions of gas collapse under gravity. If the gas is organized into sheets and filaments, it may channel material into specific regions, influencing where and how stars form. Where sheets intersect or compress, conditions may become especially favorable for the birth of new stars. Webb's ability to peer inside these clouds, rather than just observing their surfaces, is revolutionizing our understanding of how galaxies recycle their material and create new generations of stars. The light echo technique is just one of many tools astronomers use to probe the universe's structure. Measuring cosmic distances has always been a challenge. For nearby stars, astronomers use parallax, the apparent shift in a star's position as Earth orbits the Sun. But for more distant objects, the shifts become too small to detect. Instead, astronomers rely on standard candles, objects with known intrinsic brightness. By comparing how bright they appear from Earth, they can calculate their distance. Cepheid variable stars are one such standard candle. These pulsating stars have a well-defined relationship between their pulsation period and luminosity. Measure the period and you know the true brightness. Type Ia supernova are another, exploding with a consistent peak brightness that makes them reliable distance markers for galaxies far beyond the reach of parallax. Webb has validated a newer technique using stars at the tip of the red giant branch. As low-mass stars age, they swell into red giants and reach a maximum brightness before fading. This tip occurs at a consistent luminosity, providing another standard candle. Webb's infrared sensitivity makes it ideal for detecting these stars in galaxies tens of millions of light years away. Another promising method involves carbon stars, evolved stars with atmospheres rich in carbon, which have consistent colors and brightness in the near-infrared. By using multiple independent methods, astronomers can cross-check their results and ensure accuracy. A recent study combined Cepheids, red giant branch stars, and carbon stars to measure distances to 10 galaxies. All three methods agreed, yielding a Hubble constant of about 70 kilometers per second per megaparsec, a value that sits between the two conflicting measurements that created the Hubble tension. This agreement suggests the tension may be less severe than previously thought, or that the situation is more nuanced. The consistency between different techniques also validates Webb's measurements, demonstrating the telescope's reliability and precision. Refining the Hubble constant is more than an academic exercise. This number determines the universe's age, size, and ultimate fate. Every improvement in precision narrows the range of possible cosmological models and helps predict how the universe will evolve. As astronomers continue to refine these measurements, Webb's contributions will be central to resolving one of the most important questions in modern science. But distance measurements are just one piece of the puzzle. Webb is also revealing how feedback from black holes shapes the evolution of galaxies. When a supermassive black hole feeds on surrounding gas, it doesn't just pull matter inward. The infalling material heats up, radiating energy across the electromagnetic spectrum. This energy creates powerful winds that can blow gas out of the galaxy at thousands of kilometers per second. These outflows, known as feedback, play a crucial role in regulating star formation. If too much gas is expelled, the galaxy can no longer form new stars, effectively shutting down its growth. If too little gas is removed, star formation can proceed unchecked, quickly exhausting the galaxy's fuel. Webb's observations of early galaxies with overmassive black holes show clear signs of feedback in action. Spectra reveal emission lines with shapes that indicate gas moving away from the galaxy center at extreme velocities, sometimes fast enough to escape the galaxy's gravitational pull entirely. This feedback explains why some early galaxies with massive black holes remain small. The black hole grows rapidly, generating enough energy to prevent the surrounding galaxy from forming many stars. Only after the black hole's activity subsides can gas cool and collapse to form new stars, allowing the galaxy to catch up in mass. Over hundreds of millions of years, this process brings the black hole to stellar mass ratio closer to what we see in the local universe. Feedback doesn't just affect individual galaxies. Gas expelled by black holes enriches the intergalactic medium with heavy elements, which can later fall back into galaxies or fuel star formation elsewhere. This cycle connects the evolution of single galaxies to the growth of the entire cosmic web. Simulations of galaxy formation must include feedback to match observations. Without it, models predict too many massive galaxies forming too early. Webb's data is helping astronomers refine these models, revealing the complex interplay between black holes, star formation, and the cosmic environment. As Webb continues to observe galaxies at different stages of evolution, it is providing a dynamic view of how feedback shapes the universe. Some galaxies show active outflows, while others appear calm, suggesting that feedback is a temporary but transformative phase. By comparing these systems, astronomers are learning what triggers feedback, how long it lasts, and how it influences the growth of galaxies over billions of years. Yet, even as black holes sculpt their host galaxies, they also play a role in clearing away the cosmic fog that once filled the universe. The story of reionization, the process that made the universe transparent to light, remains one of the great frontiers in astronomy, and Webb is uniquely equipped to explore. While Webb's primary mission is to study the distant universe, its capabilities have also opened new windows on our cosmic neighborhood. One of the most intriguing discoveries came from observations of Alpha Centauri, our closest stellar neighbor. This system, just over 4 light years away, consists of 3 stars, Alpha Centauri A and B, which are similar to our Sun, and Proxima Centauri, a small red dwarf. Proxima is already known to host at least 2 planets, one of which orbits in the habitable zone where liquid water could exist. Detecting planets around Alpha Centauri A and B has been much more challenging. These stars are bright, and their glare overwhelms the faint signals from any orbiting planets. Ground-based telescopes have struggled to find evidence of planets in this system. But Webb, with its mid-infrared instrument and innovative observing strategies, has changed the game. By carefully blocking out the starlight and searching for faint infrared sources, astronomers detected a possible planet orbiting Alpha Centauri at about twice Earth's distance from the star. The signal is consistent with a large planet, possibly a gas giant, though further observations are needed to confirm it. If this detection is real, it would represent our closest planetary neighbor outside the solar system, aside from Proxima's small worlds. The proximity of Alpha Centauri makes it a prime target for future missions, including the possibility of direct imaging or even robotic exploration. Detailed studies of any planets in this system would provide invaluable insights into planet formation and the potential for habitability in systems similar to our own. The technique used to detect the possible planet around Alpha Centauri demonstrates Webb's versatility. Although designed to study the most distant galaxies, the telescope can also be adapted to search for planets around nearby stars. This expands Webb's scientific reach and ensures that unexpected discoveries can come from even the most familiar corners of the sky. If confirmed, the planet around Alpha Centauri A would likely have formed through the same process that built Jupiter and Saturn in our solar system, the gradual accumulation of a solid core, followed by the rapid accretion of gas from the surrounding disk. The planet's location in the habitable zone raises the tantalizing possibility that it could host large moons, some of which might be suitable for life. Detecting such moons would require even more advanced telescopes, but the discovery would mark a major milestone in the search for habitable worlds beyond our solar system. The Alpha Centauri system also serves as a test case for theories of planet formation. By comparing planets around stars similar to our Sun, astronomers can determine which aspects of our solar system are typical and which are unique. This context is essential for understanding how common planetary systems like ours might be throughout the galaxy. Webb's ability to reveal new worlds, both near and far, underscores its role as a transformative tool for astronomy. Whether it's uncovering the secrets of the first galaxies or finding planets next door, the telescope is reshaping our view of the universe at every scale. While Webb's discoveries about distant galaxies and nearby planetary systems have captured headlines, some of its most profound insights come from studying the space between stars. The interstellar medium, the gas and dust that fills the voids within galaxies, has long been a subject of fascination and mystery. Before Webb, astronomers pictured these regions as mostly smooth and featureless, with only hints of turbulence and structure. But Webb's infrared vision, especially when combined with the light echo technique, has revealed a hidden world of complexity. When a supernova explodes, its light can travel for centuries before encountering a cloud of interstellar dust. When this happens, the light illuminates the dust from within, creating a light echo that briefly reveals the internal structure of the cloud. Webb's observations of such echoes have shown that the interstellar medium is anything but uniform. Instead, it is filled with tightly packed sheets, filaments, and knots, structures as small as 400 astronomical units across, several times the size of our solar system, but still tiny compared to the vastness of space. These sheets are not random. Magnetic fields thread through the interstellar medium, and as charged particles and dust grains move, they tend to align along these invisible lines of force. Over time, this interaction sculpts the gas and dust into elongated, layered formations. Turbulence, driven by supernova explosions, stellar winds, and gravitational instabilities, stirs the material further, creating a hierarchy of structures from the largest clouds down to the smallest eddies. Understanding these structures is crucial for unraveling the process of star formation. Stars are born when dense regions of gas collapse under gravity. If the gas is organized into sheets and filaments, it may channel material into specific regions, influencing where and how stars form. Where sheets intersect or compress, conditions may become especially favorable for the birth of new stars. Webb's ability to peer inside these clouds, rather than just observing their surfaces, is revolutionizing our understanding of how galaxies recycle their material and create new generations of stars. The light echo technique is just one of many tools astronomers use to probe the universe's structure. Measuring cosmic distances has always been a challenge. For nearby stars, astronomers use parallax, the apparent shift in a star's position as Earth orbits the Sun. But for more distant objects, the shifts become too small to detect. Instead, astronomers rely on standard candles, objects with known intrinsic brightness. By comparing how bright they appear from Earth, they can calculate their distance. Cepheid variable stars are one such standard candle. These pulsating stars have a well-defined relationship between their pulsation period and luminosity. Measure the period and you know the true brightness. Type Ia supernova are another, exploding with a consistent peak brightness that makes them reliable distance markers for galaxies far beyond the reach of parallax. Webb has validated a newer technique using stars at the tip of the red giant branch. As low-mass stars age, they swell into red giants and reach a maximum brightness before fading. This tip occurs at a consistent luminosity, providing another standard candle. Webb's infrared sensitivity makes it ideal for detecting these stars in galaxies tens of millions of light years away. Another promising method involves carbon stars, evolved stars with atmospheres rich in carbon, which have consistent colors and brightness in the near infrared. By using multiple independent methods, astronomers can cross-check their results and ensure accuracy. A recent study combined Cepheids, red giant branch stars, and carbon stars to measure distances to 10 galaxies. All three methods agreed, yielding a Hubble constant of about 70 kilometers per second per megaparsec, a value that sits between the two conflicting measurements that created the Hubble tension. This agreement suggests the tension may be less severe than previously thought, or that the situation is more nuanced. The consistency between different techniques also validates Webb's measurements, demonstrating the telescope's reliability and precision. Refining the Hubble constant is more than an academic exercise. This number determines the universe's age, size, and ultimate fate. Every improvement in precision narrows the range of possible cosmological models and helps predict how the universe will evolve. As astronomers continue to refine these measurements, Webb's contributions will be central to resolving one of the most important questions in modern science. But distance measurements are just one piece of the puzzle. Webb is also revealing how feedback from black holes shapes the evolution of galaxies. When a supermassive black hole feeds on surrounding gas, it doesn't just pull matter inward. The infalling material heats up, radiating energy across the electromagnetic spectrum. This energy creates powerful winds that can blow gas out of the galaxy at thousands of kilometers per second. These outflows, known as feedback, play a crucial role in regulating star formation. If too much gas is expelled, the galaxy can no longer form new stars, effectively shutting down its growth. If too little gas is removed, star formation can proceed unchecked, quickly exhausting the galaxy's fuel. Webb's observations of early galaxies with overmassive black holes show clear signs of feedback in action. Spectra reveal emission lines with shapes that indicate gas moving away from the galaxy center at extreme velocities, sometimes fast enough to escape the galaxy's gravitational pull entirely. This feedback explains why some early galaxies with massive black holes remain small. The black hole grows rapidly, generating enough energy to prevent the surrounding galaxy from forming many stars. Only after the black hole's activity subsides can gas cool and collapse to form new stars, allowing the galaxy to catch up in mass. Over hundreds of millions of years, this process brings the black hole-to stellar mass ratio closer to what we see in the local universe. Feedback doesn't just affect individual galaxies. Gas expelled by black holes enriches the intergalactic medium with heavy elements, which can later fall back into galaxies or fuel star formation elsewhere. This cycle connects the evolution of single galaxies to the growth of the entire cosmic web. Simulations of galaxy formation must include feedback to match observations. Without it, models predict too many massive galaxies forming too early. Webb's data is helping astronomers refine these models, revealing the complex interplay between black holes, star formation, and the cosmic environment. As Webb continues to observe galaxies at different stages of evolution, it is providing a dynamic view of how feedback shapes the universe. Some galaxies show active outflows, while others appear calm, suggesting that feedback is a temporary but transformative phase. By comparing these systems, astronomers are learning what triggers feedback, how long it lasts, and how it influences the growth of galaxies over billions of years. Yet, even as black holes sculpt their host galaxies, they also play a role in clearing away the cosmic fog that once filled the universe. The story of reionization, the process that made the universe transparent to light, remains one of the great frontiers in astronomy, and Webb is uniquely equipped to explore. After the Big Bang, the universe was a hot, glowing plasma of protons and electrons. As it expanded and cooled, these particles combined to form neutral hydrogen atoms, making the universe transparent for the first time. But this transparency came with a catch. The universe was plunged into darkness, a period known as the Cosmic Dark Ages. No stars or galaxies had yet formed to light up the cosmos, and the neutral hydrogen absorbed most wavelengths of light, making the universe opaque to anything but the faintest glimmers. The dawn finally broke when the first stars ignited. Their intense ultraviolet radiation began to ionize the hydrogen around them, splitting atoms back into protons and electrons and creating expanding bubbles of ionized gas. As more stars and galaxies formed, these bubbles grew and merged, eventually reionizing the entire universe. This epoch of reionization is one of the most dramatic transitions in cosmic history, marking the end of the Dark Ages and the beginning of a universe filled with light. Understanding when and how reionization happened is crucial for piecing together the story of the first stars and galaxies. Webb was designed with this goal in mind, equipped to observe galaxies from the reionization era at redshifts between 6 and 10. These galaxies existed when the universe was only a few 100 million years old and still partially shrouded in neutral hydrogen. Some regions had already been cleared by earlier generations of stars, while others remained opaque. A key challenge in studying reionization is determining how many ionizing photons escaped from early galaxies into intergalactic space. Not all ultraviolet light produced by young stars makes it out. Some is absorbed by dust or neutral gas within the galaxy itself. Only the photons that escape can contribute to reionizing the universe. Webb spectra provide clues about this escape fraction. Certain emission line ratios indicate whether ultraviolet photons are leaking out or being trapped. Galaxies with high escape fractions show specific spectral signatures, and by identifying these, astronomers can estimate how much early galaxies contributed to reionization. Current Webb observations suggest that most early galaxies were efficient at releasing ionizing photons. Combined with the unexpectedly large number of bright galaxies found at high redshift, this implies that ordinary star-forming galaxies, not exotic sources like quasars or population Roman 3 stars, were likely the main drivers of reionization. The timeline, however, is still being refined. Most evidence points to reionization being complete by redshift 6, about a billion years after the Big Bang, but exactly when it started and how quickly it progressed remains an open question. One of the most intriguing aspects of reionization is its topology. Did the ionized bubbles grow uniformly, or did they follow the structure of the cosmic web, expanding preferentially along filaments where galaxies clustered? Simulations predict that reionization should have been patchy, with ionized regions growing faster in dense areas and voids remaining neutral longer. Webb is beginning to provide the data needed to test these predictions, mapping both the distribution of galaxies and the state of the intergalactic medium across wide swaths of sky. To study the faintest and most distant galaxies, astronomers have turned to a natural phenomenon, gravitational lensing. According to Einstein's theory of general relativity, mass bends the fabric of space-time, causing light to follow curved paths. When a massive object like a galaxy cluster sits between us and a more distant galaxy, its gravity acts as a lens, magnifying and distorting the background object. This gravitational lensing can make galaxies that would otherwise be invisible appear bright enough for detailed study. Webb systematically exploits gravitational lensing by targeting massive galaxy clusters. In a single image, the telescope can capture hundreds of lensed background galaxies, some dating back to when the universe was less than a billion years old. Without the magnification provided by the cluster, these galaxies would be far too faint to detect. Even with Webb's power, lensing not only makes the impossible possible, it also allows astronomers to study the internal structure of early galaxies in unprecedented detail. For example, one lensed galaxy observed by Webb appeared as an elongated arc stretched and brightened by the gravity of a foreground cluster. Astronomers nicknamed it Firefly Sparkle because of its appearance. When they examined it closely, they found it contained 10 distinct star clusters, each resolved as a separate bright point. These clusters had different ages and masses, indicating that star formation in the galaxy occurred in bursts rather than all at once. The total stellar mass was surprisingly low, about 10 million solar masses, a tiny fraction of the Milky Way's mass. But the galaxy's structure matched predictions for what our own galaxy might have looked like at a similar age. Firefly Sparkle and other lensed galaxies provide a snapshot of how massive galaxies like the Milky Way built up over time. Rather than forming all at once, they assembled gradually from smaller building blocks, each contributing stars and gas. The star clusters seen in these early galaxies may be the precursors of the globular clusters that orbit large galaxies today, ancient, densely packed groups of stars that have survived for billions of years. Gravitational lensing also allows astronomers to test models of dark matter. The pattern of distortion in lensed images depends on how mass is distributed in the lensing cluster, including both visible matter and dark matter. By analyzing the shapes and positions of lensed galaxies, astronomers can map the total mass of the cluster and probe the properties of dark matter itself. Combining lensing with Webb's spectroscopic capabilities opens new frontiers. The magnification provided by lensing makes it possible to obtain spectra of galaxies that would otherwise be too faint, revealing their chemical composition, star formation rates, and ionization states. These measurements provide unprecedented insight into the properties of typical galaxies during reionization, helping to answer fundamental questions about how the first structures in the universe formed and evolved. As Webb continues to push the boundaries of observation, each new discovery brings us closer to understanding the universe's earliest chapters. The telescope's ability to peer back in time, combined with the natural magnification of gravitational lensing, is transforming our view of cosmic dawn and the processes that shaped everything we see today. The discoveries made by Webb have not only pushed the boundaries of what we can see, but also deepened the mysteries that remain. Every few months, astronomers announce a new record for the most distant galaxy ever observed. Each new record holder existed closer to the Big Bang, pushing our view further back in time. The process is relentless. As Webb's deep field images accumulate, fainter and more remote objects are found, and the frontier of observable time steadily recedes. JWST held the record at redshift 14, 32 for a while, only to be surpassed by another galaxy at redshift 14, 5, and then a candidate at redshift 16. If confirmed, that would mean seeing a galaxy that formed just 250 million years after the universe began. Why does the record keep advancing? Partly, it's because Webb is still in its early years, and astronomers are only beginning to analyze the vast troves of data it produces. The deepest images require tens of hours of exposure, and not all planned deep fields have been observed yet. As more data is collected and analysis techniques improve, including the use of machine learning to sift through the images, more distant and fainter galaxies are being identified. There's also a statistical inevitability. If bright galaxies exist at redshift 14, even brighter or more massive ones likely exist at redshift 15 or 16. The universe is vast, and the earliest galaxies are simply the rarest. With enough sky surveyed, Webb is bound to find them, but there is a limit. Eventually, the search for the first galaxies will run up against the epoch before stars existed. Before redshift 20, the universe was still in its dark ages, filled only with neutral hydrogen. Webb might detect faint signals from this hydrogen, but it won't find galaxies. There simply weren't any yet. The gap between the earliest galaxies we can observe and the first stars is narrowing, and within a few years, Webb may have mapped nearly all of cosmic history from the first light to the present. Each new galaxy discovered at these extreme distances is more than just a data point. Its brightness reveals how quickly stars were forming. Its spectrum tells us about the chemical elements present. Its size and structure show how galaxies assembled. Some early galaxies look surprisingly ordinary, with star formation and chemical enrichment much like what we see today. Others are outliers, too bright, too massive, or too chemically evolved for their age. These outliers are especially valuable as they challenge our understanding and force us to refine our models of cosmic evolution. The public is captivated by these discoveries. There's something awe-inspiring about seeing light that has traveled for over 13 billion years, carrying information from the dawn of time. Each image from Webb is a window into the universe's earliest moments, making the abstract concept of cosmic history tangible and real. Yet, behind the excitement of breaking distance records lies a deeper mystery. The universe is not just expanding, but accelerating. Galaxies are moving away from each other faster now than they were billions of years ago. Something is pushing space apart with increasing strength, a phenomenon known as dark energy. This mysterious force was first discovered in the late 1990s when astronomers noticed that distant supernova appeared dimmer than expected, indicating that the expansion of the universe was speeding up. Webb's observations have confirmed and refined these findings. By studying more supernova at higher redshifts, Webb extends our measurement of cosmic expansion further back in time. The data show that dark energy has been present for billions of years, consistently driving acceleration. But what is dark energy? The simplest explanation is that it's a property of space itself, a cosmological constant that remains the same as the universe expands. As space grows, more dark energy appears, fueling faster expansion. This idea fits the data, but it raises profound questions about the nature of reality and the fate of the cosmos. Alternative theories suggest that dark energy might not be constant, but could change over time. Some models predict that it could grow stronger or weaker, or even reverse, causing the universe to collapse in a big crunch. Others propose that dark energy is a dynamic field, not a fixed property. Webb's precise measurements of cosmic expansion at different epochs are helping to test these ideas, but so far, the evidence points to a remarkably steady dark energy density. The future of the universe depends on the true nature of dark energy. If it remains constant, the expansion will continue to accelerate forever. Galaxies outside our local group will eventually recede faster than light, disappearing beyond the cosmic horizon and leaving the universe increasingly dark and empty. If dark energy grows stronger, it could eventually tear apart galaxies, stars, and even atoms in a scenario known as the Big Rip. If it weakens or reverses, gravity could one day halt the expansion and pull everything back together. For now, the data suggest a future of endless expansion, but the ultimate answer remains elusive. Webb's mission is not just about breaking records or confirming theories, it's about revealing the unexpected. The telescope has already found black holes too massive for their galaxies, galaxies too bright for their age, and star formation happening in ways that defy previous models. Each discovery forces astronomers to rethink their assumptions and expand their theories. The universe, it turns out, is richer and more complex than anyone imagined, and yet even Webb has its limits. The first 200 million years after the Big Bang remain just out of reach, as the earliest galaxies are faint and their light is stretched far into the infrared. Detecting them will require even longer exposures, more sensitive instruments, or the help of gravitational lensing to magnify their signals. Future telescopes, both on the ground and in space, are already being planned to push the frontier even further, perhaps to the very first stars themselves. For now, Webb stands at the edge of the known universe, opening a window onto cosmic dawn. Every week brings new discoveries, each one challenging what we thought we knew. The story of the cosmos is far from finished. With every observation, Webb is showing us that the universe is vaster, stranger, and more magnificent than we ever dreamed. The journey of discovery continues, and the universe, after 13.8 billion years, has finally begun to reveal its deepest secrets.